Okay, now imagine artificial neural networks as mathematical functions. These functions take inputs represented as x, weight terms like w, and constant terms c, to produce a kind of output that is interested for our research that we represented by y. So in a more mathematical form, it looks like this. Y is equal to a function of transpose of this matrix or times the w and plus c. To visualize this, think of y as the output that we want to predict or understand. It could be something like future stock price, or the credit risk of customers, or the return on an investment portfolio. Now, in this setup, X is what? X is a matrix, okay? So it collects all the variables. For instance, in financial application, these inputs might include variables like the stock prices, historical data from this customer data. So X will have what? Some rows that they represent the training samples that we use to train our networks, and columns that they represent what? The variables or features that we have in our model. So the constant term C will calibrate our model for each axis and each models that we might have. So it will make a function work just fine. So when we apply this neural network into finance, it will make us some predictions. For example, some predictions of the future price of the stocks, or the credit score of the clients, or some information that we might be interested to know about our portfolio. So the Y, as we said here, could be what? Could be the dependent variable, such as price of next term, credit risk, level of clients, or the return rate of a and the matrix X could be represented as what? X11, X12, X1n. We have also X21, 22, X2n. And the first one will represent the sample one. Second one will be sample two. And then if we consider to have k rows. It might be written as k1, k2, till kn. So it would be sample n. Okay. And here we can have the features, right? So let's say feature 1, next one, feature 2, feature n, and finally we had the k rows with the final one, sample k. So about the history of deep learning, it was started in 1952 with a stochastic gradient descent, which is employed for an optimization problem at that time. But really, it was started in 1958 by building block of the existing neural network, which are what? The perceptrons. So perceptrons developed by Rosenwald in 1958. That was a structural and the main important break of building of this building. So it was the primary important building block of the neural network, and then with adding the different layers to come up with the deep learning. So if we want to know what the perceptron really looks like, we can also, similar to what we had before, consider some inputs. So the x1, x2, let's say x3 and xn, okay? And then we have to have what? We have to have a kind of summation here. Each of these will give us a kind of input. For these inputs, we also need what? Some weights. So here, let's consider W1, W2, for X3, W3, and Wn. So they are what? They are the weights. Okay. And then by a kind of aggregation of these x's and w's, we will have summation for a j that is starting from 1 to n. Okay, so this is the sum. And finally, we have to have a kind of function, as we could see before. So basically, that is normally a step function, but it could be also different if we consider it as a activation function, okay, to let us know which part of this calculation that we had before should be activated to give us the output to have a better result from the input data. So this would be our final result or output here as the y. So for the deep learning, the simple model, as you could see, include what? An input layer, and we must have what? Also output layer, okay? But in the deep learning, we have some hidden layers also between this input and output. So these hidden layers are also hidden, okay? So for input layers, as we said, we have some inputs that we can show them as the axis, okay? It could be like x1 to xn. So these inputs will be connected to the hidden layers. And it can be connected to all of them, but not necessarily be used by the activation function for the final results. But they all contributed, and they will be checked with different combinations to see which one is really necessary for improving the results. So there are some weights, as we said also before. So the weights are also here. So we have here the different weights. We can say 1, 1, 1, 2, so on. So. And then a combination that could be discrete or continuous. So they will give us some outputs. Not necessarily equal to the input, to the number of inputs. It could be less. And then finally, they will give us what? The output that we have here, also with some weights that we can consider also for this one, okay? So the different weights also here will be considered for the first one. So let's say and then we can have the output in our output layer with also a function that is working here on all this combination of aids with the weights. Okay. So these aids that we have here do not mix up this K with that one. That's say that a J is equal to what? To a function of what the weights were here, okay, with a combination of weights and x's with a function, okay? So here also this yk is also a combination of the weights with all a's that we had here with the function. So this hidden layer could be 1, could be 2, 3, more. And when we see that the output and the quality of output is not well enough, we might like to increase the number of the hidden layers to have a better performance for the model and better outputs.